we're going to do an example problem that shows us how to use Newton's second law for a system of objects. And this time we're actually going to plug in numbers instead of just talking about it in the abstract sense. So what we have here is what's called an Atwoods machine. It's got two masses over a pulley, and what we assume is the pulley has no friction and the cord that connects these things is massless. So all we have to worry about is M1 and M2 and any forces that act on them. Okay? And just like we went through two processes before, we're going to go through and we're going to show you the two ways to do this problem. So how do we get started anytime we have a motion problem?
I always start with free body diagrams.
Excellent. Free body diagram. So how many objects we have?
We got two objects.
We've got two objects. So we're going to have to deal with two free body diagrams. Okay. So here's object 1.
Okay, we got tension.
Tension, Ft. Here's
And
object 1 also has
gravity. So we can put Fg, but we might just say Fg, but we know that's equal to mass 1 times gravity.
All right, so F1g, which is M1g. Okay. And then over here on object 2,
similarly, tension, and we know those FTs are the same.
those FTs are the same. So we're not subscripting those because those are on the same rope. They're the same.
Yep.
Okay.
And then F2g, which is M2g.
F2g, which is M2g, because that's just weight. Okay. So then we do what we did before. We've got to keep separate objects separate if we're looking at it as individual objects as opposed to a whole system. So object 1, we have net force equals mass times acceleration. So this is Newton's second law. So what do we have?
We have the tension. I'm assuming up is positive, right?
Up is positive.
Okay, so
well, now that's an interesting question. Okay. Yeah, up is positive.
Okay.
Yep, up is positive. We'll go with that.
Okay.
Okay, so net force on 1 is
Ft minus M1g.
Minus M1g equals
M1A1.
M1A1. Okay. So there's Newton's second law for this object, and we're stuck. Why are we stuck?
I don't know tension.
Okay, you don't know tension, and
I don't know acceleration.
we don't know acceleration. So we're actually trying to find the acceleration of these blocks, but I have two unknowns, and I'm stuck.
Two equations.
So we need a
Count
second
for two.
equation, right? All right. So second one.
So sum of force.
Sum of force 2.
M2A2.
M2A2, but the sum of the forces on object 2 are
almost like the last one.
Ft minus M2g instead of M1g equals M2A2.
Now are our signs reversed?
No, they don't need to be, right? Ft is positive,
Okay, Ft is
and
up. Okay.
okay, so this is okay. But sign is interesting here because A2 here versus A1 here, because we had two unknowns and so we needed two equations, but now I have three unknowns and I only have two equations.
But we know that the accelerations are the same, so I was a little bit confused on the sign, but
okay,
M2 is
no,
going,
you say the accelerations are the same,
okay,
but
they're the same, but opposite directions.
Oh, same magnitude,
Right.
opposite direction. Okay, so this side is going up,
Yeah,
but this side is
it's
going
going
down, and that's negative. Since they're connected by a string, though, like you said, same magnitude. So we actually have another equation. We have A2 equals
negative
A1. Okay, they're opposite of each other, but same size. So that means we can actually start doing a little algebra and arithmetic and getting some things worked out. Now, I like to leave everything as variables until the end and then plug in numbers at the end, so we'll do that. Okay, so starting with this equation, I'm not going to do anything except solve it for Ft. Okay, so I have Ft equals M1A1 plus M1G.
Okay.
And then I'm going to do the same thing for this green equation, except I am going to make this substitution so we can get rid of that.
Have A1 then.
Right, so then I have Ft also equals M2G minus
M2A2 or M2A1.
A1, right? Okay, so we added this over, but this became negative. Okay, but now I have Ft is equal to this whole thing and this whole thing. So I can put those two things together, and what we get is M1A1 plus M1G equals M2G minus M2A1.
Now this looks nice because we'll know the masses.
We know the masses,
we know
yep.
gravity, so
And
we
so,
can solve acceleration.
mass 1 is 3 kilograms and mass 2 is 5 kilograms. Then what we have is 3 times A1, which I don't know, plus 3 times 9.8, I can do that math, equals 5 times 9.8 minus 5 times A1. Okay, so I can combine my like terms. I'm going to add this 5A1 to that side, and I'm going to subtract that over there, which really gets me 8A1 equals 2 times 9.8.
Yep.
Okay, which is 8A1 equals 19.6. So if we divide both sides by 8, we get an acceleration of 2.45 meters per second per second. Okay, now that's A1. Look at its sign.
Okay, A1
Is
positive,
which
makes sense because it's going up.
Right, that
so
side's
then
going up.
A2 must just be negative
And
2.5.
That's what we said right here. They're the same but opposite. So this one's going to be accelerating down at 2.45 meters per second per second. Okay.
Now, if we want to know tension, we could just sub in what
Right,
we
we
know
could
now,
go,
too,
we could
and that
put
would
it
be
up
pretty
into this
easy.
equation. Now that
Yep.
we know the acceleration
Now everything
and we know
else
the
kind of
mass,
falls into place.
everything falls into place. Okay, so this is a pretty straightforward problem. Lots of steps though, and that's because we did this problem from the point of individual objects. But Newton's second law works not only on individual objects, but also on systems. Okay, so instead of looking at all those forces that were acting, we're going to look at external forces, forces that come from outside of the system. Okay, so the system is actually everything in the green line, right? We've got the two masses connected by the rope strung around a pulley. So what forces act on this system from the outside?
There's gravity.
There's gravity on this one.
Yep, and gravity on M2.
Okay, so F1G and F2G. Now, it looks like those are both pulling in the same direction, but okay, this pulley is a direction changer. So pull down over here is a pull up over here. So these are technically opposite. Okay, and since M2 is bigger, what I like to do is I like to say, well, Newton's second law says the net force equals mass times acceleration. I need to assign a direction. So let's just say that around like this is positive, since it's going to be going that way. You could pick the other way, it's not going to matter. Then my net force becomes F2G minus F1G, which equals
mass. But the mass is the mass of the system,
okay,
right?
so this is the total mass. I'm going to put MT there so we know it's the total mass times A, which is the acceleration of the system. Well, F2G is just M2G, right? So M2G minus M1G equals the total mass times the acceleration. So if this is still 3 and this is still 5, what I have is 5G minus 3G equals 8A.
Okay.
Right? Well, that's 2 times 9.8 again, because G is 9.8. That's 8A. 19.6 equals 8A. Divide by 8, divide by 8, and A equals 2.45 meters per second per second. You'll notice this is going to be in this direction. Okay, so it's going to be accelerating this way at 2.45 meters per second per second. So it kind of matters how you set up your system in terms of what your signs do, but since you're picking your system, that's okay. Okay, so that's Newton's second law for a system of objects. And when you treat groups of objects as a system instead of multiple independent objects, it tends to simplify the math, but you got to be careful that you're not forgetting something. Okay, for instance, if you had a little bit more complex of a problem where you had a cart sitting on a track and you had one pulley with a mass over here and one pulley with a mass over here, and so it was hanging like that. Okay, there's still only going to be 2 external forces because the normal force and gravity are going to balance, and you're going to have weight here and weight here. But when you go to find the total mass, there's a mass here, and there's a mass here, and there's a mass here. Okay, so you can still treat it as a system of objects. Okay, but you've got to pay attention to all the objects and all the forces.